Section 5.6, the multiplication rule for independent events. In the last section, we talked about the multiplication rule for events that were not independent, where one event affected the probability of the other. In this section, they are independent, and it gets a bit easier because we can just multiply their two probabilities together. This only applies to independent events where the probability of one event is not affected by something occurring or not occurring previously. For example, suppose the pager drives the same route to work on Monday through Friday. The route includes one traffic light, which has a 42% chance of being green, 55% chance of being red, and 3% chance of being yellow. Part A, what's the probability that the light is green on Monday and red on Tuesday? So in probability notation, we'd write it like this. And indicates that we're going to be multiplying two probabilities. There's a 42% chance that it's green on Monday, a 55% chance that it's red on Tuesday, and these probabilities are independent, meaning it doesn't matter if it's green on Monday. That's not changing the probability that the light is red on Tuesday. So we can just multiply those and we get 0.231. What's the probability that the light is red on Monday through Friday? So in other words, we need it red on Monday and Tuesday and Wednesday and Thursday and Friday. So that's just going to be that 55% for each of those 5 days, all multiplied together. And we can simplify it by writing it like that. And there's about a 5% chance that he'll see red lights every day that week. In 1986, NASA launched the Challenger space shuttle, which exploded on takeoff and killed all the crew members on board. In an investigation to determine what went wrong, scientists found that O-rings were to blame. They estimated that the probability that an O-ring would function properly was 97.7%, which seems high, but considering that this is a life and death piece of equipment, should have been much higher. To make things worse, there were 6 O-rings, and all 6 had to function properly for the shuttle to launch safely. If the O-rings are independent, what's the probability that the shuttle would launch safely? So putting it into a probability problem, we would need the first O-ring to function properly, and the second one, and the third one, all the way up to the 6th one. So it would be that 0.977 times itself 6 times, which gives an overall probability of 87%. So in other words, there was a 13% chance that this rocket would explode on takeoff just because of these O-rings, or about a 1 in 7 chance. So let's look at this problem from the opposite perspective and find the probability that at least one O-ring were to fail. And there's a lot of different ways that can happen. So we could have just one fail, or 2 of them, or 3 of them, all the way up to all 6 failing. On the opposite side, there's only one situation where we don't have at least one O-ring that fails, and that's where all 6 of them are good, all 6 of them function properly. These are complementary events. Anytime we see a problem that involves the phrase at least one, we want to treat it as a complement problem because it's easier to find the probability of just one event and subtract it from 1 than it is to find the probability of a number of different events that add up to the probability that we're looking for. So for this one, we would want to find the probability that all 6 O-rings function properly, which is the probability we found on the previous slide, and then subtract that from 1 to give the probability that at least one O-ring fails. This would be the sum of all of those different events added up. 2 events are complementary when their probabilities add to 1 and they make up the full sample space of everything that can happen. When we're talking about an event, let's call it event A, noted down here. Its complement would be denoted as A with a C subscript exponent there. And that's given by everything that's not included in event A, and its probability would be 1 minus whatever the probability of A's is. A rapid test for HIV screening quickly gives results to patients in a walk-in clinic. Rapid tests are often less accurate than the slower laboratory tests. And one particular rapid test has a probability of 0.008 of producing a false positive, where it incorrectly indicates that HIV is present in the patient. If a clinic tests 200 randomly selected people who are free of HIV antibodies, meaning they don't have HIV, what's the chance that at least one false positive will occur? We're going to assume that these tests are independent. So when we see this phrase, at least one, we want to treat it as a complement problem because there's way too many situations where at least one person will get a false positive. It could be 1 out of 200, 2 out of 200, etc., 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 all the way up to all 200 getting false positives. The only situation where we don't have at least one false positive is where we have no false positives at all. No false positives. So we're going to find the probability of that, and we're going to subtract it from 1. If we have no false positives, right, we're going to start off by saying this doesn't occur, all right, and we're dealing with the other remaining 99.2%, all right, and we want that event to occur for all 200 people, which is given here. So there's a 20.1% that all 200 people get the correct results, identifying that there is no HIV present. And the probability that at least one does get a false positive is everything that's remaining, the other almost 80%. So to recap our probability rules, when we have two events and we're finding the probability of A or B occurring, the general addition rule is to add those two probabilities together and then subtract the overlap, which is double counted. If the events are disjoint or mutually exclusive and have no outcomes in common, in other words, they don't overlap at all, in that case, we can just add the probabilities together because there is no overlap we have to subtract out. When it comes to multiplying, if the events are not independent, we use a conditional probability for that second probability. And if they are independent, we can just multiply them together. We want to make sure that we're justifying which rule we're using by identifying these events as either independent or not independent. Government data shows that 8% of adults are full-time college students and 30% of adults are age 55 or older. If we randomly select an adult, is the probability of selecting a full-time college student and someone over the age of 55 simply those two probabilities multiplied together to give us 2.4%. We're going to say it's not. In order to do this, these need to be independent events. In other words, the probability of one isn't affecting the probability of the other. If we were to pick someone and determine that they are a full-time college student, it's probably way less likely that they're 55 or older. So in that sense, knowing the probability of one event, knowing that one event occurs, that they're a full-time college student, is changing the probability of that second event. It's way less likely to occur. That being said, these are not independent events, and we're not allowed to just multiply their probabilities. Lastly, disjoint events cannot be independent and vice versa. Disjoint is when two things can't happen at the same time, also known as mutually exclusive. Independence is when we have two events that don't affect the probability of another. Let's say we have the event A, which is a person less than 10 years old, and event B, a person has a driver's license. These are disjoint events. You can't be less than 10 years old and have a driver's license. Are they independent? Does knowing one change the probability of the other occurring? It does. If we know someone's less than 10 years old, they can't have a driver's license. The probability that they have a driver's license drops to 0%. That probability changed based on the first one. Therefore, they're not independent. And because of that, two mutually exclusive events or disjoint events can't be independent.